Urban compressed air power. 1890, Paris. The owner of a restaurant in Montmartre turns a brass valve set into the wall, and air bursts from a pipe at a pressure of 6 atmospheres. He connects a hose to a pneumatic motor that powers a meat grinder. No electricity, no steam engine in the basement, just air from the municipal network, like water from the tap, and at the end of the month, a bill arrives for the cubic meters consumed. At the end of the 19th century, several European cities built what today seems like fantasy, but was then a practical solution to the problem of energy supply. Centralized compressed air networks delivered to every building through underground pipes. Paris, Birmingham, Offenbach, and Vienna laid steel pipes 10 to 30 centimeters in diameter, through which compressed air flowed continuously at 6 to 8 atmospheres, driving thousands of mechanisms across the city. Air did everything. Elevators rose and descended smoothly and silently, powered by pneumatic cylinders that carried no risk of cable failure. Workshop machinery ran on pneumatic motors that were more reliable than the electric motors of the time. Heavy shop doors opened automatically by pneumatic actuators, creating a sense of magic for customers. City clocks were synchronized by pneumatic impulses from a central chronometer, so every clock in the city showed the same time to the second. Pneumatic mail sent documents through capsules, pumps drained groundwater, theater fans circulated air. Everything ran from a single source. The Paris system was the largest of all, built by engineer Victor Pop, who in 1881 convinced city authorities that compressed air could become a universal energy source for a metropolis where electrification was still in its infancy, and steam engines in basements posed fire hazards and polluted the air with soot. By the 1890s, more than 50 kilometers of pipes stretched beneath the streets, linking 5 compressor stations to thousands of subscribers, from restaurants to banks, from bakeries to printing houses. Absolute fire safety was a critical advantage in an era when buildings had wooden floors. Lighting was gas-fueled with open flames, and a single spark could destroy entire districts. Compressed air did not burn, did not spark, and did not explode if it leaked. In the worst case, a pipe would whistle, but it posed no danger. Ease of use made the system accessible to anyone without technical training. Turn a valve, connect a hose, and energy was available instantly, like water from a tap. Then World War I broke out, and everything changed. The war industry demanded the immediate scaling of weapons production, and arms factories required enormous amounts of energy delivered quickly, in months, not years. Pneumatic systems could not handle such scale. Pressure dropped when hundreds of machines were switched on at once, and increasing compressor capacity was a slow and costly process. Electricity proved more convenient for mass production because an electric motor delivers high power in a compact form, scales easily from kilowatts to megawatts, and can be supplied from a power plant located dozens of kilometers away. Governments invested billions in building power stations and transmission lines, and this infrastructure grew explosively because war tolerated no delay. After the war, no one restored pneumatic networks because investments had already been made in electrification. Electricity won, not because it was better for civilian use. In many cases, pneumatics were simpler and safer, but because it was better for war. Afterward, inertia simply carried everything in the same direction. The Paris network lasted longer than any other, until 1994, 113 years of continuous operation. But by the end, it served only a few hundred subscribers, city clocks, and automatic doors in museums and banks. The last customer disconnected when the cost of maintaining the aging infrastructure exceeded reasonable limits, and spare parts for compressors from the 1880s simply no longer existed. Today, the principle is used locally. Hospitals move medications through pneumatic tubes, And chemical plants use pneumatics, where electricity poses an explosion risk in atmospheres filled with flammable vapors. This is the story of an alternative path of development that was destroyed not by competition, where the best technology wins, but by war, which chose electricity for its own needs and invested such resources in it that after the war, competition became impossible. And that choice, made in factories of death, determined how cities would live for the next 100 years. Steam cars, a technology destroyed by war. 1910. Boston. A milkman climbs into his Stanley steamer and turns the single control lever that regulates the flow of steam to the turbine. The car moves off so smoothly that the milk in the bottles doesn't even slosh, because the steam turbine builds speed gradually, without jerks, without gear changes, which this machine simply doesn't have. Full torque is available from 0 RPM, and the car accelerates continuously and quietly. No clutch, no gearbox, just one lever. More steam means faster, less means slower, and all control is reduced to a single hand. Steam cars had a fundamental advantage over gasoline vehicles. Full torque from 0 RPM. Steam presses on the piston with the same force regardless of rotational speed, so from a complete stop to top speed, traction was constant, making a gearbox conceptually unnecessary. An internal combustion engine, by contrast, operates only within a narrow RPM range and produces almost no power at idle, which is why it requires a complex transmission. Driving becomes a demanding skill involving coordination of clutch, throttle, gear lever, and brake. This meant radical simplification. No clutch meant dozens fewer parts. No gearbox meant hundreds fewer parts. The entire vehicle was an order of magnitude simpler and more reliable than a gasoline equivalent. Ride smoothness was unattainable for gasoline cars for decades because ICE pistons move back and forth, and every fuel explosion sends a shock through the chassis. A steam turbine rotated evenly and ran so quietly that a glass of water placed on the dashboard showed not a single ripple even at full speed. Silence was critical in urban environments. Milkmen made deliveries at 4 in the morning, and a steam van moved more quietly than a horse's footsteps, disturbing no one. A gasoline truck would have woken hundreds with its clatter. Ease of operation opened the market to women, who could not safely start gasoline cars with a hand crank. Kickback could break arms, whereas a steam car started with the turn of a key without the slightest risk. A Stanley steamer could accelerate to 100 kilometers per hour in 30 seconds, and the world speed record of 1906 to 205 kilometers per hour was set by a steam-powered car on the beach at Ormond Beach. There was, however, one problem. Starting required warming up the boiler for 15 to 40 minutes, and every morning you had to wait until the pressure gauge reached operating pressure. This drawback was tolerable before the war because the advantages outweighed the inconvenience, and many owners simply hired servants to light the boiler an hour before departure. Then World War I began. The war standardized gasoline as the #1 military fuel. Tanks, airplanes, trucks, and motorcycles all ran on gasoline engines, and governments invested billions in building oil refineries and fuel delivery infrastructure. Thousands of engineers worked to improve internal combustion engines, because every percentage point of added power meant an advantage on the battlefield. Steam car manufacturers were left without orders or funding because steam machines took too long to start and required water, something not always available in field conditions. After the war, the market was flooded with cheap surplus military trucks, selling for $200 to $500, while steam cars cost 3 to 5 times more. The Kettering electric starter eliminated the main drawback of gasoline cars, the dangerous manual crank, and starting an ICE became just as easy as starting a steam car, but instantaneous. Ford collapsed prices through assembly line production, while steam cars remained hand-built products without economies of scale. The last Stanley steamer rolled off the line in 1924, and steam cars disappeared from the roads within just a few years, so quickly that people who grew up in their era barely noticed the disappearance of a technology that was refined and possessed advantages gasoline cars would not match for another half-century. The technology did not become obsolete, nor did it stop working. The world simply chose a different path, not on the free market, where the best product wins, but on the battlefields, where what matters is what works best for war. And that choice determined what humanity would drive for the next 100 years. Gyroscopic transport, a technology taken by war, 1910. London. Along a single rail, a 10-meter-long rail car moves slowly. It doesn't fall, even though there is no second rail, and it looks like an illusion until you realize that inside, two massive gyroscopes, each weighing a ton, are spinning at 3,000 revolutions per minute. These rotating masses generate a moment so powerful that the car holds itself upright automatically. People climb into the car from one side, overloading it, and it tilts. But the gyroscopes compensate, creating an opposing moment, and the car levels itself again, as if supported by invisible hands. In reality, it's just the physics of rotation. Lewis Brennan, an Irish engineer who had earlier invented a guided torpedo for the British Navy, spent a decade developing a single-rail train because he saw it as a solution to a fundamental problem of rail transport: the cost of infrastructure. A conventional railway required two rails, a wide track bed, embankments, and bridges, all extremely expensive, especially in mountainous terrain. A monorail, by contrast, could be built at half the cost, needed a narrow track bed and slender supports. But a car on a single rail falls without stabilization, and gyroscopes were the only way to solve that problem. In 1914, Russian engineer Pyotr Shklovsky built a two-wheeled car with gyroscopic stabilization that could stand still without falling and drive at any speed, maintaining the stability of a four-wheeled vehicle with the compactness of a motorcycle. In 1932, the Italian ocean liner Conte di Savoia was equipped with 3 gyroscopes, weighing 100 tons each, reducing roll by 90%. Passengers could dine during storms without worrying about wine glasses tipping over. The technology worked flawlessly and seemed ready to change the shape of cities and transportation. Then World War I broke out, and gyroscopes went to the front. Torpedoes required gyroscopic course stabilization because without a gyroscope, a torpedo quickly drifted off course under the influence of currents and missed its target. With a gyroscope, it ran straight and struck ships from kilometers away, turning submarines into a deadly threat. Gyrocompasses were indispensable for warships because magnetic compasses lie on steel hulls, while a gyrocompass finds true north through the rotation of the Earth. The gyroscopic artificial horizon showed pilots where up and down were in clouds, saving thousands of lives and turning aviation into a decisive weapon of war. All manufacturing capacity and all engineers who understood gyroscopy were mobilized for military production, and civilian projects were left without resources. The government denied Brennan funding, reassigned his engineers to torpedo work, and the gyroscopic train prototype slowly rusted away in a yard until it was dismantled for scrap. Shklovsky was trapped in Russia amid revolution and civil war. The prototype was lost, and he himself immigrated to England, where, without funding, he was unable to build another. After the war, civilian gyroscopic projects were not revived because gyroscopes became defense products, dual-use technologies controlled by military authorities. Any attempt to purchase a powerful gyroscope for civilian purposes invited a visit from security services. The war gave rise to mass assembly line production of conventional cars and trains built to standardized designs, and gyroscopic systems remained bespoke, expensive, experimental, ill-suited to an industry that had already chosen a different direction. Today, gyroscopes have returned to our lives, but on a miniature scale. They are in every smartphone and drone, and Segways and electric unicycles use the same self-balancing principle as Brennan's railcar a century ago. But the large-scale applications the pioneers dreamed of, gyro trains, gyro cars, gyro-stabilized ships, were never realized. War took the technology, used it for killing, and never allowed it to return to its civilian purpose. The path back was blocked by secrecy, control, and the inertia of an industry that had already chosen another route of development. Factories without electricity. Mechanical power networks, 1900. Mechanical power networks, how shafts and belts powered industry. A textile mill in Manchester. When you open the door to the workshop, you're hit by a wall of sound. 5 meters overhead, steel shafts, thick as pillars, and as long as the entire hall, spin continuously. Dozens of leather belts hang down from them to the machines below. The belts slap, pulleys squeal, looms pound, and all of it forms a single organism whose heart beats in the next room, where a house-sized steam engine turns the main shaft that powers everything else. This was the standard system in factories before mass electrification. A single energy source, a steam engine, or a water wheel, rotated shafts that transmitted power through belts and pulleys to every machine. Electric motors were expensive, unreliable, and rare, and installing a separate steam engine for each machine was absurd. The main shaft ran the length of the workshop, spinning constantly in bearings mounted near the ceiling. From it spread a three-dimensional network of intermediate shafts and belts, with each machine connected by a leather belt ranging from a few centimeters to half a meter in width. A worker didn't turn a machine on with a button, but mechanically. Each machine had a working pulley and an idler pulley. When the belt rested on the idler, the machine stood still. A lever shifted the belt onto the working pulley, and the machine came to life. No electricity, just pure mechanics. Transmission efficiency reached 70 to 80%. Some energy was lost to bearing friction and belt slippage, but steam engines were so powerful that the surplus easily compensated for these losses. Reliability was high because the mechanics were simple. Shafts, belts, pulleys, and breakdowns were rare. Repairs didn't require specialists. A hammer, a wrench, and a new belt, and work continued. Electricity, by contrast, demanded understanding the invisible, current, voltage, resistance, while mechanics were visible and intuitive to anyone. But the drawbacks were horrific. Exposed shafts spun overhead, belts lashed through the air. If clothing caught, a person was dragged into the machinery. If a hand was pulled in, it was torn off. Women's long hair posed a deadly risk. Thousands of workers lost fingers, arms, and lives every year. Stopping the main shaft halted the entire workshop. A failure of the steam engine shut down the whole factory. It was impossible to stop one section while keeping others running, because everything was tied into a single system. The noise was inhuman. Workers went deaf within years and communicated with gestures. Fires were a constant catastrophe. Leather and fabric belts ignited instantly, and a single spark could turn a factory into a bonfire within minutes. Then World War I began, and everything changed fundamentally. Military factories demanded modularity. One day, they had to produce rifles, the next, shells, the day after aircraft engines. The line shaft system couldn't be quickly reconfigured, nor could one section be shut down while others kept running. Electric motors offered exactly the flexibility needed. Each machine had its own motor and could operate independently. If one failed, the others kept working. Reconfiguring a section no longer required stopping the entire factory. Governments built power plants and ran transmission lines to arms factories, investing enormous sums because war demanded the speed and flexibility electricity provided, something shafts could not. By the end of the war, the advantages of electrification were obvious. Safety improved as enclosed motors replaced exposed shafts. Noise levels dropped. Flexibility became unmatched. By the 1920s, most factories were electrified. By the 1930s, line shaft systems survived only in older plants that simply lacked the money to modernize. Today, industrial museums restore line shaft systems, and a few historic factories are kept operational for visitors. The steam engine is fired up, the shafts begin to turn, belts slap, and thunder fills the workshop. The sounds of the Industrial Revolution, never again heard in a real working factory. The system powered industrialization for an entire century and built the modern world. Yet it vanished within 2 decades, not because it failed, but because war demanded the flexibility electricity provided. And the world adopted this technology not because it was best for peaceful life, but because it was best for war. Civilian mechanical computing machines. 1935. New York. On a desk sits a device the size of a typewriter, made of hundreds of gleaming gears, shafts, and levers. As the engineer enters data by turning knobs and setting dials, the mechanism comes alive with a soft clicking sound. Shafts rotate, pointers slowly creep toward their positions, and after a minute, the calculation is complete. The needle indicates the exact solution to a differential equation describing the deflection of a bridge beam under load. There is not a single electronic component inside this machine, only metal and mathematics. Mechanical computing devices existed long before electronic computers and solved complex problems in minutes that would have required hours of manual calculation. Planimeters measured the areas of irregular shapes on drawings, which was critical for surveyors and architects. Mechanical integrators solved integral equations physically. Babbage's difference engine could compute functions with precision of up to 30 digits. These machines were used everywhere. Civilian shipping relied on mechanical navigation calculators to compute courses by the stars. Engineers designed bridges and dams using mechanical integrators. Astronomers calculated comet orbits on analog machines that modeled celestial motion through systems of gears. Insurance companies used them to compute actuarial tables and determine premiums. The advantages were obvious. Reliability did not depend on electrical power. The machine worked by turning a crank, and if the power went out, the mechanical computer kept calculating. Repairs were trivial. A broken gear could be machined on a lathe, and any competent mechanic could handle it, whereas electronics required specialists. Longevity was measured in decades because metal does not degrade the way electronics do, and the transparency of the process allowed engineers to see intermediate results, understand them, and verify calculations, something impossible with electronic systems. Then World War I broke out, and everything changed instantly. Artillery required precise ballistic calculations over distances of tens of kilometers, accounting for dozens of variables: wind, temperature, barrel wear. Mechanical computing devices were the only way to perform these calculations fast enough, so all manufacturing capacity was redirected to military orders. Navigation for warships became a classified field, research was sealed, and message encryption demanded mechanical devices whose very existence was hidden from the public. World War II intensified this trend many times over. Mechanical computers became critical components of military hardware. Fire control systems for tanks, bombers, anti-aircraft guns, and torpedoes all relied on mechanical computation that worked where electronics was unreliable. Engineers were mobilized into military projects, and their knowledge became state secrets. After the war, computing machines remained defense products. The technologies did not return to the civilian market because everything related to ballistics and cryptography was classified. Attempts to purchase a precise mechanical integrator for a civilian engineering firm were denied. Electronic computers followed a similar path at first. ENIAC computed firing tables, Colossus broke German ciphers, and only decades later entered civilian life. Mechanical computers, by contrast, simply vanished. Companies shut down or shifted entirely to military contracts and never returned to peacetime production. Today, museums preserve mechanical computing machines as artifacts of an era when mathematics was embodied in metal. Collectors restore old devices found in attics, and when the gears begin turning again after 80 years, it proves that mechanics do not age. The principles survive in high-complication clocks that compute lunar phases through gear trains, but large-scale applications are gone forever. War took this technology for killing, and when it ended, it never gave it back, sealing the knowledge and destroying an entire branch of engineering, not because it became obsolete, but because war takes and does not return. Navigation and communication. Before radio, technologies destroyed by war. 1840. A hill outside Paris. At the summit stands a 20-meter-tall wooden tower fitted with a system of levers and flags. When the operator spots a signal on a tower 10 kilometers away, he quickly sets his own levers to the same position and looks to the next tower to confirm the signal has been received. A message races across France through a chain of hundreds of towers. What a courier on horseback would deliver in a week is transmitted in 20 minutes, because light is faster than a horse. The Chappe optical telegraph system was built in 1792, when revolutionary France needed rapid communication with its armies on the borders. The Paris-Toulon line stretched 800 kilometers through 556 towers, each within line of sight of the next. In clear weather, a message covered the entire distance in 20 minutes, an astonishing speed in an era when the only alternative was a galloping rider. Maritime navigation relied entirely on mechanical instruments without a single electronic component. The sextant measured the angle between the horizon and the stars, and combined with a precise chronometer, that angle became coordinates accurate to within a kilometer, enough for safe ocean passage. Lighthouses ran on oil and kerosene. Each had a unique flash pattern, and sailors identified their position by matching the beacon to a reference book. Leading marks along coastlines showed safe channels, 2 markers set at different distances, and when they lined up, the captain knew the ship was on course. The entire system worked without electronics, just paint and geometry. The advantages were fundamental. Optical signals cannot be jammed, unlike radio, which is vulnerable to interference. Secrecy was inherent. To read a semaphore message, you had to be in direct line of sight of the towers. An enemy beyond the horizon saw nothing. The system worked whenever there was light and an operator, and it was completely immune to magnetic storms and all the phenomena that disable electronics. But war changed priorities forever. The military chose radio for obvious reasons. It worked beyond the horizon, in fog, at night, and in any weather, when visual systems went blind. Semaphore networks required thousands of operators across hundreds of towers who had to be fed and paid, while radio required a single operator carrying a portable set on his back. The 2 world wars poured billions into radio technology because armies needed instant communication over any distance. States built radio stations, trained radio operators, and developed new frequencies. After the wars, visual navigation infrastructure was simply not restored. Semaphore towers stood abandoned. Maintaining hundreds of operators made no economic sense when a radio message could be sent in seconds at almost no cost. Towers were dismantled or left to rot. By the 1950s, radio navigation had taken over civilian shipping. Alternative systems were declared obsolete, not because they had stopped working, but because the world decided radio was more convenient. Today, lighthouses still shine along dangerous coasts, but mostly as backup systems in case GPS fails. Sextants are taught in maritime academies as an archaic skill, just in case all electronics go down. An entire branch of navigation disappeared, not because it was ineffective, but because war chose radio, invested enormous resources in it, and made it the standard. When the war ended, there was no way back. The infrastructure was gone, specialists retrained, investments irreversibly spent, and the world burned the bridges leading to other paths of development. Electric trucks. The forgotten standard of urban logistics, 1915. 4 o'clock in the morning. The streets of New York are empty and dark, and only the quiet hum of electric motors breaks the silence as dozens of white vans glide along the pavement, stopping at every house. Drivers carry bottles of milk to the doors and return to their cabs, and everything happens in near silence because electric motors don't roar or spew clouds of foul exhaust that would wake an entire block. The city sleeps, and the milkmen finish their routes using a technology perfectly suited to the job. In the 1910s, thousands of electric delivery vans operated in major cities, delivering milk, bread, mail, and newspapers. This wasn't an exotic novelty. It was the standard of urban logistics for companies that valued reliability. Walker Electric, Detroit Electric, and Baker Electric produced hundreds of trucks each year for dairies, bakeries, and postal services. These vans worked day after day, moving goods at a time when gasoline trucks were still temperamental machines. A range of 50 to 80 kilometers was more than enough for city routes with a 10-kilometer radius. Charging happened overnight at depots, where rows of vans were plugged into fixed chargers, and by morning the batteries were full. Maintenance was minimal, monthly bearing lubrication, and a quick electrolyte check that took 10 minutes. Silence was a critical advantage for early morning deliveries. An electric van moved more quietly than a horse's footsteps, disturbing no one. A gasoline truck, by contrast, required hand cranking with the risk of kickback and would have woken hundreds. The absence of exhaust fumes mattered for food transport. Milk and bread stayed fresh, and the simplicity of operation meant anyone could learn to drive an electric van in an hour without wrestling with a clutch or carburetor. Then World War I began. Oil became the #1 strategic resource. Tanks, trucks, and aircraft ran on gasoline, and governments invested billions in developing internal combustion engines and oil refining. Electricity simply didn't fit into the military system. Power grids didn't exist outside cities. Batteries couldn't provide hundreds of kilometers of range, and the entire military infrastructure was built around liquid fuel. After the war, the civilian market was flooded with cheap surplus military trucks, selling for $200 to $500. Business owners who had once paid $3,000 for an electric van saw only one logical choice. Economics was ruthless. The network of gas stations built with wartime money now served all civilian transport, while charging an electric truck outside the city was impossible. Electric vehicle manufacturers shut down one after another. Baker Electric in 1916, Walker Electric in 1920. By the early 1930s, the last electric vans vanished from the streets, and the technology was forgotten for 70 years. Entire generations grew up unaware that electric trucks had once been the standard, not a futuristic novelty. Today, history is repeating itself with striking precision. Amazon has ordered 100,000 electric delivery vans. UPS and FedEx are switching to electric vehicles for urban delivery. The same routes, the same logic. Quiet operation in residential areas and low operating costs. The difference is that now electric trucks are backed by political will and decarbonization subsidies, and cities are introducing zero-emission zones, turning the technology from a choice into a necessity. Electric trucks didn't disappear because they stopped working, but because war chose oil, poured billions into it, and created an economy where gasoline was artificially cheap. Between the two eras of electric trucks lies a century that began not in the marketplace, but on the battlefield. Compact steam power stations. The forgotten clean energy of cities, the basement of a large office building in Chicago. In a spacious room stands a compact steam turbine about the size of a car, quietly humming as it spins a generator and produces electricity for the entire building. Nearby, a boiler runs on anthracite, an expensive but nearly smokeless coal. The steam isn't vented into the atmosphere. It passes through a condenser, turns back into water, and returns to the boiler. The heat released during condensation is fed into the building's radiators for heating. A single installation provides both electricity and heat, releasing almost nothing into the city air. Until the 1920s, many large buildings, hotels, hospitals, office complexes, had their own steam power stations in their basements because centralized grids were unreliable or simply didn't exist. Owners preferred the independence of on-site generation. Clean-burning anthracite allowed nearly smokeless operation. Scrubbers cleaned exhaust gases by passing them through water curtains. Condensation systems returned water to the boiler, reducing water consumption by a factor of 100. The efficiency of a small station was lower than that of large power plants, around 20% versus 30 to 40. But cogeneration made up the difference. Buildings received not only electricity, but also heat from energy that large plants simply dumped. Total efficiency reached 60 to 70%. The advantages were obvious. A building kept operating even when the city grid went down, critical for hospitals and hotels. Short transmission lines within the building meant minimal losses, while centralized grids lost up to 20% of energy over dozens of kilometers of wiring. Cogeneration saved money by solving two problems with one system, and fast startup allowed stations to be switched on during peak hours when electricity prices were highest. Then war arrived, and everything changed. The military-industrial complex demanded enormous power for factories and shipyards that had to be built in months. Governments chose large, centralized power plants on city outskirts, where cheap coal could be burned in massive quantities without concern for smoke, because environmental impact no longer mattered when victory was at stake. Energy standardization required a single grid with uniform parameters, and small autonomous stations didn't fit. They complicated control. The military wanted centralized oversight to redistribute power, and independent on-site stations interfered with that control. After the war, governments continued building large power plants using the same logic. Economies of scale were real, and large plant technologies advanced faster because they received all the investment. Small stations were labeled inefficient, even though in terms of total energy use, they were often more efficient. Regulations imposed increasingly strict emission standards that small installations couldn't meet without costly upgrades. At the same time, centralized grids became more reliable through scale and subsidies. By the 1930s, most buildings were connected to municipal grids. By the 1950s, small steam stations survived only at isolated facilities. Today, the world is returning to distributed generation with striking irony. Hospitals and universities install cogeneration systems based on the same principles used a century ago, now with gas turbines and computer control. They produce electricity and heat simultaneously, deliver high efficiency, and provide independence from the grid. The only difference is that today they're called innovative, even though they replicate a standard that existed before war-centralized energy systems. Compact steam stations didn't disappear because they stopped working, but because war demanded scale and sacrificed environmental concerns for speed. The system built for war became the new normal for peace, and it's worth recognizing that this outcome was not inevitable. Military logic simply overpowered civilian needs. Mechanical energy storage, a forgotten future. That already existed 1955, the Swiss town of Yverdon. A bus pulls up to a stop with a strange structure featuring a rotating shaft. When it stops, the driver lowers a coupling mechanism that connects the bus's flywheel to the flywheel of the station. 3 seconds of metal screaming against metal, sparks flying, and the flywheel inside the bus spins up to 3,000 revolutions per minute, storing enough kinetic energy to travel 6 kilometers to the next stop. No batteries, no fuel, just the rotation of a steel disc weighing 1.5 tons, sealed inside a vacuum housing. Mechanical energy storage relies on 3 physical principles to store energy without chemical reactions: spinning flywheels, lifting masses against gravity, and compressing air in tanks. Flywheel systems were the pinnacle of this approach. Efficiency reached 95%, compared to 70 to 75% for lead-acid batteries, and service life was virtually unlimited because metal does not degrade with charge-discharge cycles the way battery electrodes do. Gravitational storage used the most predictable force of all. Water towers were essentially gravitational batteries, pumping water up at night and releasing its energy during the day. Mine hoists with counterweights reduced energy consumption by 40 to 50%, and these systems operated for centuries. Pneumatic locomotives in mines and chemical plants produce no emissions other than cold, clean air and could be refilled in 10 minutes. The advantages were fundamental: an infinite number of cycles without degradation, trivial maintenance. A broken bearing can be replaced with a hammer and a wrench, while a battery can only be thrown away. And absolute environmental cleanliness. No lead, no acid, no lithium, just metal and air. But war set different priorities. Tanks, aircraft, and submarines needed lightweight, compact energy sources, and a 1.5-ton flywheel was completely unacceptable in machines where every kilogram mattered. Batteries lost on efficiency and longevity, but won on compactness. You just connect wires and energy is available. Submarines became the main driver of battery development because they needed power underwater, where diesel engines couldn't operate. Governments invested billions in improving chemical energy storage, building massive production capacities that, after the war, took over the entire market. Mechanical storage was declared obsolete, even though it outperformed batteries in efficiency, simply because it didn't fit the new paradigm. Switzerland's gyro buses stopped operating in the 1960s, not because they failed, but because the manufacturer shut down and spare parts became unavailable. Converting them to batteries required a complete redesign that cost more than buying new diesel buses. Today, history is looping back. Beacon Power builds grid-scale storage facilities using hundreds of flywheels and vacuum chambers on magnetic bearings to stabilize power grids. Energy Vault lifts 35-ton concrete blocks to heights of 120 meters, storing gravitational energy. Literally the same concept as mine hoists 200 years ago. Compressed air storage is built in salt caverns. All of these technologies are called innovations, even though they are simply reviving what existed long before computers. Flywheels, gravity, and compressed air were ideal for stationary systems, where durability and environmental cleanliness matter. But military logic chose a universal solution that works everywhere, even if it is worse than specialized solutions for specific tasks. The world lived with the consequences of that choice for 70 years, until the environmental crisis and the problem of battery disposal forced humanity to remember and reinvent what had existed long ago. Architecture as an engineering system. Passive architecture. How buildings cooled themselves without electricity, 1850. Yazd, Persia. Outside, the temperature approaches 50 degrees Celsius. The air so hot it's hard to breathe. Inside the house, it's cool, because above the roof, rises a 10-meter-high tower with 4 open faces. Even a weak wind strikes one face, flows down the shaft, cools against damp walls, and enters the room as a cold stream, pushing warm air out through other shafts. The indoor temperature is 20 degrees lower than outside. Not a single mechanism, no electricity, just form and an understanding of physics. Before air conditioning, architecture itself was an engineering system of climate control. Building shape, orientation, wall materials, and window placement created comfort without technical devices. Thick stone or adobe walls acted as thermal buffers. They heated slowly during the day, blocking heat from entering, and released it back at night. A stone house with 60-centimeter thick walls maintained a constant temperature of 20 degrees, while outside temperatures fluctuated between 5 and 35. Architects carefully controlled window orientation. South-facing windows maximized sunlight in winter, when the sun was low, and minimized it in summer, when roof overhangs provided shade. High ceilings and ventilation shafts created convection. Hot air rose and escaped through roof lanterns, while cooler air was drawn in through windows. Inner courtyards with fountains used evaporation for cooling, working better the hotter and drier the climate. White walls in Mediterranean villages reflected up to 80% of solar radiation, while dark roofs in northern homes absorbed maximum heat in winter. Then war changed everything. Reinforced concrete became the dominant material because factories and barracks had to be built in weeks. Rectangular boxes with flat roofs, minimal windows, no towers, or thoughtful orientation. War demanded standardized solutions that could be replicated without thinking. Military barracks became the prototype for post-war housing. Architects knew only one way to build quickly, the way military facilities were built, and principles meant for temporary soldier housing were applied to permanent civilian dwellings, despite entirely different comfort requirements. After the war, air conditioning and central heating solved the problem, allowing architecture to forget passive systems. Form became arbitrary, driven by aesthetics and fashion rather than physics and climate, because technology compensated for everything. Glass skyscrapers, symbols of modern architecture, require enormous cooling systems, consuming megawatts of power simply to offset the consequences of designs that ignore solar physics. Today, movements toward passive design, such as the Passive House Standard and bioclimatic architecture, are trying to restore forgotten principles, where buildings maintain comfort with minimal energy use. But industry inertia is massive. Developers know how to build fast to military-derived standards and don't want to relearn, while buyers are accustomed to technology solving everything. The Persian wind tower cooled desert homes without electricity for 1,000 years, and could do so for another 1,000. Yet a modern architect will build a glass box and install air conditioning, because that's how they were trained and because it's faster. Even though humanity pays for this choice with resources and a climate crisis partly created by buildings that require colossal amounts of energy just to remain habitable.